Okay, so here is the 6.1 to 6.2 review sheet that I'm going to go over finding antiderivatives. I'm not going to show you the slope field stuff from the first page. I think you guys can take a look at the key and see how I got those. So for 3A, what we have to do on this one, remember, U substitution is not necessary everywhere. So on this particular problem, since there's no multiplication or division, really, you can't even use U substitution, so we're just going to find the antiderivative of all these things individually. The most common mistake here is on the first term, 1 over 2x to the fifth. People often take the 2 up to the numerator when they write that with a negative exponent, but that is not correct, so it's x to the negative fifth over 2. And then plus 6x to the fourth minus, there it is, 3x to the 1/2. Again, you'll have to excuse some of the messiness because using explain everything is not as easy as notability, at least not for me. And now we can do power rule, so add 1 to our power, which is x to the negative fourth. And then divide by that same number, which is divided by negative 4, and then we still have the times 2, which was a constant from above. Same thing here, we have a constant of 6, add 1 to our power, divide by that same number, and then minus 3 times, add 1 to 1/2, which is 3/2, and divide by that same number, so dividing by 3/2, which is the same as multiplying by 2/3, which if you look at the actual key, you'll see that that simplifies down to a 2. So I'm not going to simplify that just to save some time. You can take a look at the key to see that. All right. B. Again, you don't need U substitution on some of these. I'm going to use U substitution, assuming that you guys used U substitution, but if you can do these without U substitution, then by all means go ahead. But this is U equals 4x plus 5. So our du is equal to 4 dx. So I'm going to explain this on this problem, but then I'm just going to do it on the other problems. So remember, since du is 4 dx, I need a times 4 on the inside. But to cancel out that 4, I'm going to put a 1/4 out front. And so putting the 4 on the inside gives me my du. So now I can replace 4 dx with du. So when I substitute, this becomes 1/4 times the integral of 3 over square root of u du. Okay, and then you can take out the 3 and make this 3/4. Actually, I'll just erase the previous line here. Except it won't let me, so never mind. So this is 3/4 times the integral of u to the negative 1/2 du. Again, doing power rule gives us 3/4 u to the 1/2, add 1 and divide by the same number, plus c, substitute your u back in, so it's 4x plus 5, and then you can simplify the fraction. You do need to simplify these, so to save time making the video, I'm just going to refer you to the key that I made by hand for the final answers. Okay, C. Again, you don't need U substitution on this problem necessarily, but if you personally need it, then you probably would make u be 6x. So our du is 6 dx. To get a 6, to be consistent, I'm just going to multiply by 6 on the inside, put a 1/6 out front. Okay? I'm not going to show that anymore, but that's what happens on most of these problems where our du is equal to a number times dx. So now this becomes, by factoring out the 3 as well that's in front, I end up with 1/2 times the integral of secant u tangent u du. And then the antiderivative of that is 1/2. The antiderivative of secant tangent is just secant of u, where my u is 6x, plus c. So 1/2 secant of 6x plus c. So that is the final answer on that one. Part D, u equals 3x plus 1. That is not a very good 3. Let's try that again. U equals 3x plus 1. So du is equal to 3 dx. So I need a 3 on the inside, and therefore a 1/3 out front. And that becomes 6e to the u du. Taking out the 6 gives me 2 times the integral of e to the u, which is just e to the u, and u is 3x plus 1. So we get 2e to the 3x plus 1 plus c. Again, I'm starting to skip some steps a little bit here, but they are steps that I explained on the previous problems. So on E, we're going to let u be 2x plus 1. Du then is 2 dx. So I'm going to take the 6 out, and I'm also going to multiply by 1/2 times the integral of 1 over u to the 5th du. Find the antiderivative, so we get 3, and then 1 over u to the 5th is the same as u to the negative 5th. So I'm just going to rewrite that as u to the negative 5th. Using power rule, add 1, so I get u to the negative 4th over 4. And then you can substitute 2x plus 1 back in for u and then a plus c. I don't care if you leave your answers with negative exponents or if you write it in the denominator or whatever. But remember, that's actually, I'm going to not box that in because that is not the final answer. The final answer is you got to substitute your u back in. So just take this, plug it in right there, and then you're done. Again, refer to the hard copy of the key, or the digital copy of the key, rather, to see the final answer if you need to. On F, let u be x squared plus x, and then our du is 2x plus 1. If I factor a 3 out of the numerator in the original integral, I get 3 times the integral of 2x plus 1 over x squared plus x dx. And so, sorry, du is 2x plus 1 dx. So my du does in fact exist in this problem. So this becomes 3 times the integral of du over u, which is equal to 3 times the natural log of the absolute value of u, which is x squared plus x plus c. So that is our final answer there. On G, now here, this is actually like sine of 3x and then plus 2. So our angle is only 3x. If it wasn't, it would be impossible because our cosine of 3x here doesn't have the same angle as if it was sine of 3x plus 2 as part of the angle. So you can't actually, you wouldn't be able to do anything. So we'll let our u be sine of 3x plus 2. And then du is, don't forget chain rule, so it's 3 cosine of 3x, and then the derivative of 2 is just 0, so that's gone. And then we have our dx. So rewriting the original integral, I need a 3 on the inside, so I'm going to put a 1/3 in front. So it becomes 1/3 times the integral of u to the 4th du. The antiderivative of that, using power rule once again, is going to be u to the 5th over 5. and then we'll have our plus c. You should multiply the 1/3 times 1/5 to get 1/15, and then once again substitute our u back into our final answer. Now h, this is the problem that closely resembles tangent inverse. And so to make it look like tangent inverse, we need to take out a 5 and a 4 from the top and bottom to make that 1 over 1 plus x squared over 4 dx. Now remember, x squared over 4 can be rewritten as x over 2 quantity squared. So this is x over 2, that whole thing squared. That allows us to see that u needs to be x over 2. Remember, we're trying to make this of the form tangent inverse, the derivative tangent inverse. So our du is then 1/2 dx. I don't have a 1/2, so I'm going to put a 1/2 in there and multiply by 2 out front. So it becomes 2 times 5/4 times the integral of 1 over 1 plus u squared du. So that's 10/4 or 5/2. So you get 5/2 times tangent inverse of u, where u is x over 2, plus c. Okay. Part I, we'll let u be 9 minus 2x. So then du is equal to negative 2 dx. So then I need a negative 1/2 in front, so I can put a negative 2 on the inside. So it's negative 1/2 times the integral of 1 over u cubed du. And then we can find the antiderivative of this by using power rule again. It's u to the negative 3rd. So it's negative 1/2, add 1 to our power, which makes it u to the negative 2, divided by negative 2. And then we'll have a plus c, and again substitute our u back into there into your final answer. Part J, we're going to look at u equals natural log of x, because du then is going to be 1 over x dx, which is good because that's what we have right here, so that's our du. So our new integral then becomes the integral of u cubed du, which then becomes, so the antiderivative of that is just u to the 4th over 4, and our u is natural log of x, so our final answer then becomes natural log of x to the 4th all over 4 plus c. Letter K, we'll let u be sine of 2x, and then our du will be 2 cosine of 2x dx. So since we need a 2 up there, I'll put a 1/2 in front and take out the 6 at the same time. So it becomes 6 times 1/2 times the integral of du over u to the 4th, or 1 over u to the 4th du. Some of you might know another way to do this rather than do 6 times 1/2. You might realize 6 is 2 times 3 and you just factor out a 3. That's an okay way to do it. I'm trying to make the key based on how I think most people will have done the problem. So now this is just 3, and it's u to the negative 4th, so add 1 to your power and you get u to the negative 3rd, and then divide by that same number, so divide by negative 3, and then that equals negative u to the negative 3rd, so it's negative sine to the negative 3rd of 2x, and then plus c. On the key I wrote, like instead of negative x1, sometimes I wrote wrote the answer in the denominator. It does not matter to me which way you do that. Now the easiest way to do tangent is just to know the antiderivative rule for tangent, which is negative natural log of the absolute value of cosine of 5x. Now, since we have this 5x in here, when you do the derivative, you would multiply by 5. So if I'm doing the antiderivative, I need to multiply by 1/5 to cancel that out. Or take a look at the key, and you can see how I did it using u substitution, but you need to write it in terms of sine and cosine and go from there. Part M will let u be x to the 4th plus 2. So our du is 4x cubed dx. We need a 4 inside the integral, so I'll put a 1/4 out front to cancel that out, times the integral of u to the 5th du. And then the antiderivative of that gets me 1 to the 4th u to the 6th over 6 plus c, and again, substitute your u back into there for your final answer. Do 1/4 times 1/6 and make that 24. And then n, let's box this off here. So on n, we'll let u be 3x squared. So then our du is 6x dx. We have x dx, here's our x, here's our dx, but we need a 6. So I'll put a 1/6 out in front to balance that out. And so we get 1/6 times the integral of sine u du. The antiderivative of that is negative cosine, so it's negative 1/6 cosine of u, which is 3x squared, and then plus c. Okay, that brings us to number 4, the initial value problem. Now, when your derivative doesn't have two variables in it, you don't need to separate the variables. We just find the antiderivative right away. So y equals, antiderivative is x cubed minus 2x and then plus c. Plug in our initial condition, f of negative 1 equals 2. So we get 2 equals negative 1 cubed minus 2 times negative 1 plus c. Solving that gets us c equals 1. And so our final answer is just y equals x cubed minus 2x plus 1. Okay, moving on to the last couple problems here. So solve the initial value problem on number 5. Now our derivative has two different variables, so this is where we have to separate the variables. So it becomes dy over y plus 1 is equal to 2x plus 1 dx. Find the antiderivative of both sides. Natural log of absolute value of y plus 1 equals x squared plus x plus c. Plug in our initial condition. So I'm plugging in negative 1 for x and 1 for y. So I get natural log of 2 is equal to 1 minus 1 plus c. So my c value is natural log of 2. So c equals natural log of 2. So my equation now becomes natural log of absolute value of y plus 1 equals x squared plus x plus natural log of 2. Write that in exponential form, and we get e to the x squared plus x plus natural log of 2 equals absolute value of y plus 1. So I can drop the absolute value and put a plus or minus over here. From the stuff we talked about earlier this week and last week, we know that this can be simplified into, I can subtract 1, so it's negative 1 plus or minus 2e to the x squared plus x is equal to y. Let's make that squared look more like a 2, hopefully. better. And then we have to choose the plus or minus that when I plug in -1 for x, gets me 1 for y. So it's going to be, when I plug in -1, I get e to the 0, which is 1. So in my final answer, I'm going to need -1 plus. So -1 plus 2. And that makes sure that when I plug in -1 for x, I get a positive 1 for y. If you did -1 minus 2, you would get -3, which is not right. Number 6, u substitution, and then integrate it from u of b to u of a. Here we can do, let u be 2x minus 3. And then du is equal to 2 dx. So we can rewrite the integral as being the integral 1/2, because we need a 2 on the inside, so 1/2 out front to cancel it out, of 1 over u du. Now here, 2 and 5 on our bounds are x values, so if we plug those in for x right there, we'll get our u values for our bounds when the integral is with respect to u. So if I plug in 2 for x, u equals 1, and when I plug in 5 for x, I get 7. So now when I find my antiderivative, which is 1/2 natural log of absolute value of u, I don't need to substitute my 2x minus 3 back in. I can just evaluate this from 1 to 7, because those are u values. And that gets me 1/2 natural log of 7 minus 1/2 natural log of 1. Natural log of 1 is 0, so our final answer is just 1/2 natural log of 7. Okay, number 7, we already talked about. You could just know the derivative rule for this is negative natural log of the absolute value of cosine of x. And then plus c. Again, that's a little trickier if it's like tangent of 5x, because then I would need a 1/5 out in front, and well, a negative 1/5. When it's something like sine squared, there's a trig identity you have to use to be able to integrate it. There's nothing we can do substitution-wise, so sine squared x is equal to 1 minus cosine of 2x over 2, which is the same thing as saying 1/2 times 1 minus cosine 2x. So to do this problem, rather than integrate the original given problem, you need to find the integral of 1/2 1 minus cosine 2x dx. I'll leave you the key. You can look at the hard copy of the key for that to figure that one out. C, the tricky part here is just to realize the whole idea of these is that you can manipulate them to figure out the integral. You should know that 1 over sine is the same as cosecant. So this is, the original problem is actually just equal to the integral of cosecant squared x dx. And you should know that the antiderivative of cosecant squared is negative cotangent x, and then plus c. On D, a lot of people try to choose a u and they let it be x or x plus 2, and then they run into a problem because their dx would just equal 1d, or du equals dx, and so you have an extra x in the problem. But really all you have to do here is distribute, and you get x squared plus 2x dx, and now you can find the antiderivative of just both of those terms. And then E, again, this one's really tricky. I think this would be difficult to realize what to do on your own. But the idea is that even though some integrals seem really difficult, you can algebraically manipulate them to make them possible. So on this one, what you have to do is multiply by secant x plus tangent x over secant x plus tangent x. And what that ends up giving us is secant squared x plus secant x tangent x on the top, all over secant x plus tangent x on the bottom. And so this is what we're finding the integral of. And then let u be the denominator, secant x plus tangent x. And then our du is the entire numerator. So I'm not going to write it out, but all this is equal to du. So in the end, this just becomes the integral of du over u which is equal to the natural log of the absolute value of u, where u is secant x plus tangent x, and then squeeze a plus c in there for our final answer. And that's it.